Hello everybody, in this video we will review some tools from multivariable calculus that will be useful in our study of spherical geometry. And we begin by reviewing spherical coordinates. So in order to do this, let's just remind ourselves quickly about polar coordinates. So let me just draw a little picture here. X, Y are the two axes, and then if we take a point somewhere with coordinates x, y, this is the x coordinate and this is the y coordinate, then the polar coordinates are given by the distance of that point from the origin and the angle that this the ray connecting the origin with the point forms with the x-axis. And the standard formulas for these coordinates are, well, you can sort of see, right, that you can use trigonometric functions, that x divided by r, this is of course a right triangle here, so is this, that x divided by r is cosine theta, so x is equal to r cosine theta, and y is equal to r sine theta. Or vice versa, you see that r being the length, the distance from the origin to the point xy, is just the square root of x squared plus y squared, while tangent of theta is equal to y over x. I am specifically not writing theta as arctangent of y over x because that doesn't quite work. Arctangent is only defined, will only give you angles between minus pi halves and pi halves, while you need here the entire range from 0 to 2 pi, right? R is a positive real number and theta ranges between 0 and 2 pi. Sorry. So you will be, this actually allows you to compute the tangent of the angle, and then you can figure out the angle by knowing where the point exactly is on the plane. So spherical coordinates are sort of like the polar coordinates, but you add an extra dimension. And sometimes what confuses people is the orientation of the x and y axis. So here's the x-axis, here's the y-axis. So you see, if I were to build the polar coordinates, if I want a point that has both x and y coordinate being positive, it's going to lie here on this side rather than here. And on top of this, right, we build another axis here. So okay, namely the z-axis. Of course, the axes also go towards negative values, but here, just for clarity of the picture, I'm only drawing these positive directions. So suppose I have a point x, y, z somewhere here. So what you do is you can connect this point with the origin, and that's going to be the distance r here. And the first thing that you can do is you can project this point down onto the xy plane. So if you do that, you're going to get a point on the xy plane whose coordinates are going to be x, y, and 0. And to this point, you can just use the polar coordinates. Right? So this point has some distance from the origin. Let me just denote this distance by rho. And then there is the angle theta somewhere. And now we have to think about where this theta is. Note that the angle theta is between the x-axis and the line on the xy plane that connects the origin with the point. So it's the angle between the x-axis and that line. So theta is actually here. Okay? And now to make this look like that, because it's standard to denote the distance of a point in three-dimensional space to the origin by r, as is to denote the distance of a point in two-dimensional space to the origin. But we're more interested now in spherical coordinates. I'm going to change all the r's here to rho's, so to remain completely consistent with this other picture. So this is a rho here, and this is rho, rho, and rho. Okay, so what you need to know about this point is how it projects down onto this plane. That will give you two of these coordinates, and then the third one would be this angle here, which we call phi. Now you might want to note that in some books the angles phi and theta are switched. This one is called phi, this one's called theta. But people use different notation for different things. Sometimes these angles are called u and v, like in the book, for example. So you shouldn't just be attached to the particular notation, but rather to the definitions. Okay, so how do we get these coordinates? So what is x? Well, I can use the polar coordinates for x. So x is rho at cosine theta, just using the polar coordinates, and y is rho sine theta. So now, I want it, of course, in terms of r, theta, and phi, not in terms of rho. So I need to know how to express rho in terms of the other data. But note that the angle between the z-axis and this ray rho is right angle. So that means this complementary angle here, that's pi halves minus phi. Yeah, it's kind of difficult to draw this all on a two-dimensional picture, but remember that this angle here is actually, it sticks out of the board, right, and sort of forms this right angle here. Okay, so this allows us to say what rho is in terms of all the other angles. What do we have here? What do we have? A right triangle. This angle here is right. Again, because this lies on the xy plane and then this is completely vertical. So I have a right triangle right here. And if I use this right triangle, I see that in that right triangle, rho divided by r is cosine of that angle. So rho is equal to r cosine of pi halves minus phi. Right? Again, this is a right angle. This is a right triangle. The right angle is here. This is the hypotenuse. So if I do rho divided by r, I get cosine of this angle. So that means rho is equal to that cosine, which is the same as r sine phi. So this gives us a complete formula for x and y. So I get that x is equal to r sine phi cosine theta. Same for y. Y is equal to r sine phi sine theta. And what's left is I just need a formula for z. However, there is another right triangle here, namely here, right? That's the z coordinate coming from this point. And again, the right angle is here. So this is the hypotenuse of this right triangle. Remember, this point sticks out a little bit, right? So it's like a right triangle that goes out like that. So this, so I get that sine of, cosine of phi is z divided by r. So z is therefore So z is r cosine. Okay, and this gives us the so-called spherical coordinates. Now, what are the ranges of these variables? R is any positive real number. The angle theta is the angle that you get from the shadow of this line segment when you project it down onto the xy plane. So it exactly changes the same as this theta. So it's an angle between 0 and 2 pi. On the other hand, phi goes from the z-axis all the way down to the bottom half of the z-axis. So phi changes between 0 and pi. You can also write, and I leave this to you, an equation backwards. So r is easy because r is just the distance from the origin. That's just x squared plus y squared plus z squared. We're actually going to talk about the distance in a moment. As for all the others, cosine of phi, you just get this from this formula. That's just z over r. And then the last thing is tangent of theta. Well, that you get essentially from here. So, okay, I told you can just do it by yourself, but I actually just did it for you. Okay, so this is the translation back. And the one last thing that I wanted to say is that spherical coordinates, just like polar coordinates, are very good when you deal with circles. Spherical coordinates are very good when you deal with spheres. And the equation of a sphere, so let me just put this here, equation of the sphere centered at the origin of radius r is 1 in Cartesian coordinates that's going to be x squared plus y squared plus z squared equals r. But in polar coordinates, it's particularly simple. It's just r equals to r. Right? So that means you want, so this is a variable, and this big R is a constant. You want the distance of all the points that lie on the sphere to be the same. This is the distance from the origin to be R. Okay, so much about spherical coordinates. I wanted to say just one word, well, one sentence, a few sentences about the distance in R3, essentially just by giving you a formula that you're all familiar with and that I sort of already implicitly used when talking about spherical coordinates. So, I seem to have lost a lot of my pens. 2, distance in R3. So, given 2 points, P equal to x1, y1, z1, and Q, whose Cartesian coordinates are x2, y2, z2, the distance between P and Q is given by the square root of it essentially just follows from the Pythagorean theorem. Okay, so let's move on to parametrically given curves. in R3. It is so that it's very useful to give a formula for a curve in R3 by giving a parameter. So what is such a curve? So such a curve is a function, I call it C for curve, from some interval or the real numbers. Yeah? The domain could be a closed interval or it could be the real numbers. Sometimes it could even be the open interval into R3. So in other words, if the domain is the real numbers or an interval, then it has only one variable here. So if we don't denote it by t, the output is three variables, x, y, and z, and they each depend on t. So let's look at some examples. So in other words, this curve is given by these three equations: x of t is equal to t, y of t is equal to t, and z of t is equal to t. So what will be the graph of it? So that means I have x of t equal to t, and that's also equal to y of t, z of t. So the equation of c in x, y, z is x equal to y equal to z. So it's actually a line. This is a line that says every time you make a step in the x direction, you make the same step in the y direction, the same step in the z direction. When t is 0, I get the origin. Again, this is the x, y, and z. When x is 0, I get the origin. When t is 0, I get the origin. When t is 1, I get the point 1, 1, 1. When t is 2, I get the point 2, 2, 2, and so on. So it's the line that looks like this. Of course, this line sort of sticks out of the board. Goes the same. It forms, equal angle with each of the axes. Let's look at another example. And I only want to give a few simple examples here. This is not a course in multivariable calculus, but some of them, it's kind of useful to remind ourselves about these things. So 2, another curve from R to R3, given by c of t is equal to t squared 0. If I want to think about it, what it means in the x, y, z coordinates, you see that the z coordinate stays 0 all the time. So that means the image of this function, so the curve, is completely contained in the xy plane. And when you think about it, since x is equal to t and y is equal to t squared, we get that y is equal to x squared. So we actually get a parabola. It's a parabola that's contained entirely in the xy plane. I'm only drawing half of it. The other half is here on the other side. Okay, and the parabola does not go anywhere into the z direction. It actually lies completely in the plane z equals 0, so it lies in the xy plane. Let's modify this a little bit. Let's look at now a curve given by, I'm sorry, it should be capital C. C of t equal to t squared. So what's happening here? Well, in order to be able to visualize this, it is very often good to first project onto two coordinates in which this thing looks relatively simple, and then sort of add the movement in the third coordinate later. So when I project it onto the xy coordinate, on the xy plane, so the projection onto xy plane is the curve that's just given as t comma t, so that is x and this is y, so that's the line y equals x. Okay, so here in orange I'm going to draw a shadow of this curve down here. It's a line like this. This is the line y equals x. This is not the graph of this curve, this is just a shadow of it in the xy plane. If you imagine the sun shining directly vertically in the z direction, so this will be the shadow of the curve. So what happens now as you include the z coordinate, you see the z coordinate changes with the square of t. So that means this is actually a parabola that lies, whose shadow is this line, and sort of goes up like this. It goes up in the z direction, but when you look at it, when you look at this from the top, you just get this line. Okay, let's look at another example. So this is sort of an interesting one. C of t equal to cosine 2 pi t sine 2 pi t t. So let's try to figure out what this is, and again I'll start with doing the projection. So in the xy plane, I just get the function cosine 2 pi t sine 2 pi t. And you may want to think about what is this in the xy plane. Well, note the x coordinate, when I square it and square the y coordinate, I get cosine squared plus sine squared, I get 1. So that means it satisfies equation x squared plus y squared equals to 1. So that's a circle. So that's a circle in the xy plane. So, okay, this time I'm going to try to draw the whole thing. Yes, I know it doesn't look like a circle, but in this case I'm actually justified because we're looking at the circle from an angle. Still doesn't look good, but even with that. But you shouldn't just draw it completely circular because you're sort of looking at it. It's flat, right? It lies completely in the xy plane. So now what does the last coordinate tell me? It tells me that as I traverse the circle, the z coordinate grows. So let's just think about where we start. Where is t equal to 0? So when t is equal to 0, I get cosine 0. So t equal to 0. So c of 0 gives me cosine 0, sine 0, 0. So that's 1, 0, 0. So I am here. This is the 1, 0, 0. What happens afterwards? As t starts increasing into the positive numbers, just slightly bigger than 0, then both cosine and sine become positive. So that means I'm moving on the circle towards, and I'm first in the area of this xy plane where both x and y are positive. So that means I must be moving in this direction. So I put the 2 pi t here so that we see when t changes from 0 to 1, you make a full circle. Yeah, cosine of, when t is equal to 1, you again get cosine 2 pi, sine 2 pi, and that's the same as cosine 0, sine 0, so you're going back to that point. However, what happens to the z-coordinate? Well, by the time we get from 0 to 1, the z-coordinate has grown from 0 to 1. So it's not exactly a circle. You start out here, but then you sort of go around, getting higher every time. And as you come back, you're at height 1 and continue doing so. Okay, and the same thing happens as you go down. So this is a spiral. So you start with t equals 0, and you see the shadow is always that circle. It looks like when the sun is shining from the vertical direction down the z-axis, in the xy axis you just traverse that circle at a constant speed. But if you include the vertical movement, then every time you traverse the circle once, you go up by 1 unit. So this gives you a spiral. Okay, and finally, a very important thing for us will be length of curves in R3, because as we discussed it in the last video, we want to talk about geodesics, and geodesics are the curves that have the smallest possible length, so we need to define the length of a curve. So, length of curves in R3. And I'm just going to use a very basic derivation. So suppose I have a curve in R3, and I take 2 points that are very close to each other. Okay, on my picture, I'm not going to draw them that close because it'll be difficult to read, but imagine that they're really close. So they have some. So I'm going to do it now in R2, okay, in R2, to just not cloud the picture. So here is the change in x between the 2 points, and here's the change in y. So the length, let's call this point P and Q, of curve between P and Q, if P and Q are very close to each other, equals approximately the square root of delta x squared plus delta y squared. That's just Pythagorean theorem. That means if P and Q are really close, then the curve between these 2 points doesn't curve very much. It kind of looks like a straight line. That's of course only an approximation, but in the end, when we do Riemann sums, we take the limit and the approximation actually becomes true. Okay, so in R3, I'm not going to draw a picture here, but in R3, you get the approximate length to be delta x squared plus delta y squared plus delta z squared. Okay, and that's the same as I'm just going to introduce another parameter, delta t. Note, it doesn't matter what delta t here is, right? This is just formally true. And whenever it's a positive real number, then this is just a simple algebraic cancellation. So you get something like that. So if the curve, so now let's see be a parametrically given curve. Such that the functions x of t, y of t, z of t are differentiable. So they have derivatives. So such curves are called smooth curves, i.e. C is a smooth curve. Note that this doesn't actually even require any multivariable calculus because x of t is just a function of one variable, t. So is y and so is z. So if I assume that, then from this you see that as delta t goes to 0, then delta x over delta t approaches the derivative of x at t and finally delta z over delta t approaches the derivative. Now this should be noted here that there is some point here between these 2 points which corresponds to t0, and then these should be evaluated at t0 at this point. But I don't want to pretend here that I'm deriving this in complete detail, this formula. I just wanted you to see where this actually comes from. So one gets that the length of C between t equal to t1 and t equal to t2